The first one is on-off controller. On-off controller. Have you seen any on-off controller? On-off controller. The fridge is working on-off controller. Fridge. Iron box. Iron box. Even that AC unit, the air conditioning unit, that is also working on-off controller. These are all working on-off controller. If you see the response, when you implement an on-off controller, let us say that we are fixing the room temperature, say 24 degrees centigrade. Indian standard. European standard 18 degrees centigrade. So 24 degrees centigrade. Initially, it is at a higher temperature. So initially it is at say 30 degrees centigrade. Room temperature. If you turn on the AC, what will happen? The temperature will fall. When it crosses 24, if set point is 24, means what will happen? AC will be turned off. Am I correct or no? Because set point is 24 degrees centigrade. It decreases from 30 degrees centigrade. When it crosses 24, it will be turned off. AC will be turned off. What will happen? It will stop here or further decrease will be there. What will happen? There will be a slight further decrease. There will be a further decrease because where you are putting the sensor is important. To sense that room temperature, where you put not that our place, maybe somewhere else in the unit itself. That's why the room temperature, there will be a further fall because of inertia in that. There will be a further fall. At this point, it is turned off. After some time, what will happen? The temperature starts again, increases. That's why it will go up. Now, again, at this point, it will be on. Up to this, if you draw the controller characteristics, it will be on. It will be on up to this point. Up to this point, it will be on. This is off. Again, it will be turned on at this point. So if again it will not stop here, there will be a further increase in temperature even though you turned on. Can you expect immediately? 24, you cannot expect. That's why there will be a further increase. Once after some time, it starts decreasing. When it falls here, if you draw the characteristics, again it will be turned off. What happens? Again, there will be a further decrease. Further decrease. But AC is off. That's why again it starts increasing. As soon as it crosses, again it will be turned on. Again it turned on. Like that. On, off. Continuously it will happen. Whether the temperature settled at 24? No. It is wandering around. It is wandering around 24 degree. It is wandering. The cross variable is wandering. The cross variable is wandering around 74 degrees centigrade. That is one of the drawbacks of on-off control. One of the drawbacks of on-off control. Another problem is if this undershoot is very less or overshoot is very less, what will happen? Suppose I am having very fast process, say small time constant process I am having. For example, voltage regulator. Where you are using a voltage regulator, you'll put one servo regulator for a AC unit or some fridge, and all you will put some AC regulator. In that, they will put some set point, say 220 volt set point. Suppose incoming voltage is less than that 220 volt, means it will add more. It is single auto transformer will be there that will adjust the number of windings so that voltage will be maintained 220. Let us assume that if I add one winding, it exceeds 220, let us assume. Number of windings, auto transformer, number of windings will be there. Say some 400 windings are there. The inlet is given about 300 or 250, 500 windings are there. At 250, we are giving. It will be like this. Auto transformer means a single winding will be there. Here you are giving input. Input is given here. Whatever the voltage coming is given here. Now it is 219.5 is coming. What is required? 220. Let us assume 220. So what will happen that the tapping taken is here. The output will be taken like this. Output. This is the output. As number of windings increases, voltage will increase. That is the idea. Not a transformer. Number of windings increases, voltage will increase. But a minimum of one winding can be included. Let us assume. If one winding will introduce 1 volt, that is also let us assume. If this carbon brush will include one winding because it is less than 220. Less than 220. 219.5. So it include one winding. What will happen? 220.5. It exceeds. That's why it will reduce. The controller will try to reduce. It reduces one winding. Again, it becomes 219.5. Again, it will increase. It becomes 220.5. So it oscillates between these two. That is called chattering. That is called chattering. The chattering problem may come in on-off control. There are two problems. One is wandering around set point. It never settles at set point. It will wander around set point. 24 degrees centigrade means it will wander around set point. It will be either above or below the set point, not at the set point. Second problem is if the incoming is very close to the set point, it cannot adjust that much precise. That's why it will toggle between on and off, on and off. That is called chattering. You can notice this in a servo regulator at home. They put there will be a sound, chattering sound you can notice, and that problem is called continuous on and off, on and off, on and off. That is called chattering. That problem may come. One more problem is there. That is called fatigue failure. Fatigue failure. You know that suppose on a sheet of metal is there. If you again and again, if you fold, what will happen finally? It will break into two pieces. That is called fatigue failure. That is called fatigue failure. Here, you are subjecting this the final control element continuously on, off, on, off, on, off. That's why, like chattering, on, off, on, off, on, off. That's why it may fail. Fatigue failure may happen. Fatigue failure may happen. So these are the three drawbacks. First one is wandering around set point. Second one is chattering. And third one is fatigue failure. These are the three drawbacks with the on-off controller. How we can reduce this? How to reduce this chattering and fatigue failure? Wandering we cannot remove. Wandering we cannot remove. Well, always wandering will be there. But we can remove that chattering, and we can reduce fatigue failure. We can, by removing chattering, we can reduce fatigue failure. If you remove chattering, stress will be less. That's why you can reduce fatigue failure. So how that we'll see now. Let us assume that I am having a temperature bath. Here, a heater is used to heat this. A heater, this is the heater coil, a resistance coil that will give heat to that liquid bath. A constant volume liquid bath. You want to maintain this at some temperature T, say 60 degrees centigrade. For that, you are comparing this with the set point. This is PV. You are subtracting that PV. You will get an error as an output. If you subtract cross variable from set point, you will get the error. The error is given to the on-off controller. This is the on-off controller. This is the on-off controller. This is the characteristics of on-off controller. If the error is positive, on. If the error is negative, off. This is off. This is on. So you are giving this to a on-off controller. The error is given to the on-off controller. Power is given to the on-off controller. The power will be turned. It will work like a switch. On-off control is nothing but a switch. So on-off controller will turn on and off. So initially, let us assume that it is the water bath. It is at room temperature, say 30 degrees centigrade. Say set point is 60 degrees centigrade. So what will happen? Initially, error is 60 minus 30, 30 positive error. That's why the switch is turned on. That's why it will increase. It approaches the set point. As soon as it crosses at 60, it will be immediately turned off. But let us assume that it has inertia, because sensor is here, heater is here. That's why to understand the inertia, I am telling this example. Where heat is produced, the bottom. Sensor is in the middle of the level. Sensor is in the middle of the level. Heat is produced here. The sensor senses 60 degree means what is the temperature here? Hotspot temperature may be 200 degrees centigrade. The coil temperature may be 200. But here, the liquid temperature may be about 70 or 80. Suppose you are putting stirrer means, stirrer, if you put a stirrer inside, somewhat uniform temperature, somewhat, not exactly, but anyhow, there will be a difference. Here it may be 70, here it may be 60. That's why, because of the stirrer, but turned off, heater is turned off as soon as it crosses 60 degree, but stirrer, again it is running. That's why it makes uniform. That's why there will be a further increase in temperature above 60 degree. But after some time, because of ambient temperature, it starts decreasing. After some time, it starts decreasing. As soon as it falls just below 60 degrees, it will be again turned on. But now only it is turned on. It has to reach that sensor. It takes some distance. The temperature has to reach there. That's why during that time, there will be a further fall. Further fall, not this much increase. Small fall. Then again, it turns this way. Again, the error becomes positive. That's why again turned on. So it will be like this. Is wandering around set point, but overshoot is more than undershoot. If the time constant of the process is very less, as we have seen in servo response, then it will be like this. Chattering will happen like this. But here it has a very large amount of liquid. That's why the distance between the heater and sensor have an inertia. That's why it takes long time to reach. That's why this oscillation will be there. It will wander. But I don't like this many number of on and off because of to avoid fatigue failure and chattering. I want to avoid chattering. Sometimes it may happen. That's why I want to avoid chattering. And this, I am introducing a differential gap. I am introducing a differential gap. Differential gap means here, what is the set point? 60 degrees centigrade. But I am telling a tolerance of 2 degrees centigrade, 58 degrees centigrade and 62 degrees centigrade. 62 degrees centigrade. If it is within that 58 and 62, I am assuming that it is within that limit. I am giving a bandwidth. The set point is in terms of bandwidth. Set point is from 58 to 62, not a single set point. Why? To avoid chattering. To avoid chattering. How it works now, let us assume. Here, if we introduce a differential gap, this is called the controller with the differential gap. Here, if you turn on, if you turn on the system, what will happen? Now the temperature is at 30 degrees centigrade. That's why heat is turned on. What will happen? The temperature will increase, but within that limit, 58 to 62, it is within that limit. That's why controller, the on-off controller will not turn off because it is within that limit. It is on, it is within that limit. That's why it won't say anything. It came inside, but it further increase because heater is on. Further increase. When it crosses 62, just it crosses 62, here at this point, it will be turned off. At 62 only, it will be turned off. So therefore, here it goes up to 63, let us assume. Now it will go up to 66 because here we turned on at 60, but here we turned off. Here we turned off at 60, but here we turned off only at 62. That's why there will be a further increase in temperature. Further increase in temperature. Deviation will be large. Then it starts decreasing because that heater is turned off. When it comes within that band, it will not change its state. Controller remains off only. Controller remains off only because it is off. That's why there will be a further decrease. When it just crosses 58 and fall below, again it will be turned on. Again it will be turned on. At this point only it will be turned on. When it is turned off, at this point it is turned off. It is turned on now only. Now only it is turned on. But because of inertia, it will come down slightly. Then it will turn upwards and goes up. So here it won't turn off. Where it will turn off? Here only it will turn off. So if you draw the characteristics for the controller, up to this it is on. Up to this it is on. It will be off here. It is off here. Again, it will be on at this point. Suppose you are not using the differential gap, means where it will be turned off. Where it will be turned off. It will be turned off here itself. Here itself it will be turned off. Where it will be turned. That's why you can expect that there will be a lesser overshoot. When it falls below 60, again it will be turned on here. Again it will be turned on here. Blue line is with the differential gap. Now we are talking about without differential gap. Now it goes like this. That's why at this point again it will be turned off. Again it goes up and falls below 60 degree. Again it will be turned on. With the differential gap, how many times it turned on and off? One off, one on only. But without differential gap here, it is turned off, turned on, turned off, turned on 3 times. Only 2 times on and off. With we can reduce the number of on and off by introducing a differential gap. So because of the differential gap, number of on and off reduces. That's why we can reduce the fatigue failure at the cost of large deviation. Wandering is more. Earlier, it goes up to slightly goes up above the set point, up to 63 we have seen. Now it goes up to 66. Now it goes up to 66. So if you introduce a differential gap, wandering will be more. Magnitude of wandering will be more. Magnitude of wandering will be more, but number of wandering will be reduced. Number of wandering, number of on and off of the controller can be reduced. But the permanent drawback is you cannot stop the wandering. It never settles at set point. That's why we can introduce, we'll see in the next class.